In this video, we'll learn about multiplying polynomials in Foundations of Mathematics and Pre-Calculus 10. In Math 10, your child will continue to extend their understanding of operations with numbers to operations with algebraic expressions. Polynomials are algebraic expressions with one or more terms. Each of these terms has a coefficient, variable, and whole number power. Note that some of these are implied. We strongly encourage you to watch our Math 9 polynomials video prior to this one. That video addresses representing, adding, and subtracting polynomials, as well as multiplying and dividing by monomials, or single terms. Let's begin by playing with arithmetic. Pick two whole numbers between 1 and 10 that differ by 2. For example, I'll pick 5 and 7. Now, multiply them. Next, square the whole number between the two numbers that you picked. For me, that's 6. 6 squared is 36. What do you notice? No matter what two numbers you chose, whether 4 and 6 or 8 and 10, their product is always 1 less than the square of the number between them. Why? Understanding operations on polynomials can help us generalize and explain this result. We'll return to this question at the end of this video, but first we'll revisit multiplying numbers. How many do you see? How do you see them? You might have counted all of the donuts using multiplication. There are 7 rows of 6 donuts. 7 times 6 is 42. An arrangement of objects in rows and columns is called an array. Arrays can be a very helpful way to think about multiplication. We can also imagine multiplication as the area of a rectangle that measures 7 units by 6 units. We call this an area model. There are many ways that you might have counted these donuts. You might have noticed the different variety of donuts and taken this into account. 7 and 6 can be partitioned into 5 and 2 and 5 and 1, respectively. 7 times 6 is equivalent to 5 plus 2 times 5 plus 1. We can see 5 rows of 5 chocolate donuts, 5 rows of 1 glazed donut, 2 rows of 5 glazed donuts, and 2 rows of 1 strawberry donut. Symbolically, this can be expressed as multiplying 5 by 5, 5 by 1, 2 by 5, and 2 by 1. The product is the sum of these partial products. This is called the distributive property. Adding the partial products gives us 42 once more. This method of determining the product can also be represented by removing the pictures of the donuts and recording each partial product in the appropriate space. Next, we'll review how these concepts help us make sense of two-digit multiplication and later, binomial multiplication. Consider 23 times 14. 23 can be partitioned into 20 and 3. 14 can be partitioned into 10 and 4. Place value is just one convenient way of decomposing two-digit numbers. 23 times 14 can be written as 20 plus 3 times 10 plus 4. 20 is multiplied across both 10 and 4. Similarly, 3 is distributed across both 10 and 4. Each part of 23 is multiplied by every part of 14. The 4 partial products add to 322. Before we turn our attention to algebra, let's look at how an area model helps us make sense of an algorithm from arithmetic. 4 times 3 is 12. 4 times 20 is 80. 10 times 3 is 30. And 10 times 20 is 200. The sum, once more, is 322. A standard algorithm tells us to focus on digits more so than place value. The 1 in carry the 1 comes from the 10 in 12. Back to algebra. A quick reminder from the first video. A small off-white square has dimensions of 1 unit by 1 unit. It's called a 1-tile or unit tile. A green rectangle also has a width of 1 unit. Its length is arbitrary and labeled x. We call this an x-tile. A blue tile also has a length of x. Because it's a square, its width is equal to its length, so its dimensions are x units by x units. We call this an x-squared tile. Red tiles represent negative terms, opposites to the positive terms on the left. Next up, multiplying binomials. A binomial is a polynomial having 2 terms. Think bicycle, bilingual, or biceps. How might thinking about 23 times 14 help you determine 2x plus 3 times x plus 4? Like 2-digit numbers, there's a natural way to partition binomials, not by place value, but by terms, separated by plus or minus signs. And like 2-digit numbers, an area model can help us determine the product of 2 binomials. The 2x from the first binomial is distributed across both x and 4. 2x times x is 2x squared. 2x times 4 is 8x. Similarly, 3 is multiplied across both x and 4. 3 times x is 3x, and 3 times 4 is 12. Each term of the first polynomial is multiplied by every term of the second. 2 of the 4 partial products can be combined. 8x plus 3x is 11x, so the product is 2x squared plus 11x plus 12. This polynomial has 3 terms. It's called a trinomial. Let's try another. What is the product of x minus 5 and x minus 2? Once more, we'll think about area. Some learners find it helpful to set up guides for the dimensions. We can represent side lengths of x minus 5 and x minus 2 by lining up positive x tiles and negative 1 tiles. Each term of x minus 5 is multiplied by every term of x minus 2. X times x is x squared. X times negative 2 is negative 2x. Negative 5 times x is negative 5x. And negative 5 times negative 2 is positive 10. It's important to remember to distribute the sign of each term. Again, the middle 2 terms can be combined. Negative 2x and negative 5x make negative 7x. The product of x minus 5 and x minus 2 is x squared minus 7x plus 10. Let's examine this further. These 2 algebraic expressions are equivalent. That is, although they look different, one is expressed as a product, the other is expressed as a sum, they are equal for any value of x. For example, what if x were 6? In each expression, 6 is substituted for x. Evaluating the expression on the left gives 4, as does the expression on the right. When x is 6, each expression is equal to 4. We correctly multiplied x minus 5 by x minus 2. Take a moment to think about these 2 expressions. What is the same? What's different? X plus 3 squared means that there are 2 factors of x plus 3. X plus 3 times x minus 3 also contains two binomial factors. Further, x plus 3 is common to both expressions. In the expression on the left, there's a plus sign between terms within each binomial. In the expression on the right, these signs are opposites, plus 3 and minus 3. Here are the products for each, represented both pictorially and symbolically. What do you notice? Can you spot any new similarities and differences? You might have noticed that the first term in each product is x squared, and the last term in each product is 3 squared, or 9. On the left, 9 is positive because it's the product of the same integer, and on the right, 9 is negative because it's the product of opposite integers. The product on the left is a trinomial. Its middle term is determined by doubling the product of the terms within the binomial, here doubling x times 3. This special product is called a perfect square trinomial. The product on the right, on the other hand, is a binomial. Its middle terms, negative 3x and positive 3x, are opposites and add to 0. This special product is called a difference of squares. In this next activity, we'll explore and generalize a pattern. How might you count the number of blocks in each figure? You might have noticed that each figure is made up of layers of squares. The side lengths of these squares measure 2 units by 2 units in figure 1, 3 by 3 in figure 2, and 4 by 4 in figure 3. To determine the number of blocks in each figure, multiply by the number of layers, 3 in figure 1, 4 in figure 2, and 5 in figure 3. Carry out each calculation as follows. How can we generalize this pattern? How can we express this pattern as a polynomial? Notice that the side lengths of the squares are 1 more than the figure number. So, if the figure number is n, the side length of the square is n plus 1. The number of layers in each figure is 2 more than the figure number. So, the height of figure n is n plus 2. Multiplying these 3 binomials gives the number of cubes for any figure number. The number of cubes in figure n is n plus 1 squared times n plus 2. To express this as a polynomial, we can first square n plus 1, then multiply the result by n plus 2. N plus 1 squared is equal to n squared plus 2n plus 1. We can determine this product by distributing n plus 1 across itself, or by calling upon the perfect square pattern discussed in the previous example. This presents a new challenge, multiplying a trinomial by a binomial. Once more, each term of the first polynomial is multiplied by every term of the second polynomial, or vice versa. Collecting like terms gives n cubed plus 4n squared plus 5n plus 2. These two algebraic expressions are equivalent for all values of n. For example, if n is 10, then each expression is equal to 1,452. Next, we'll apply our understanding of multiplying polynomials. The ratio of length to width of a pool is 2 to 1. A 2-meter wide concrete deck is built around the perimeter of the pool. Express the footprint of the pool as a polynomial. That is, write an algebraic expression that represents the area of the pool, including its surrounding deck. We'll let W represent the width of the pool. If the ratio of length to width is 2 to 1, then the length must be 2W. A 2-meter deck around the perimeter of the pool adds 4 meters to each dimension. The area of the pool and deck is determined by multiplying the total length, 2W plus 4, by the total width, w plus 4. Multiplying each term of the length by every term of the width gives 2w squared plus 12w plus 16. We can see these terms in the different parts that compose the total area. The area of the pool, including the surrounding deck, can be expressed as 2x squared plus 12x plus 16. This problem should not be confused with a real-world application of mathematics. You'd be hard-pressed to find a pool installer who'd calculate area in this way. The familiar context is used to help your child make sense of mathematics, not the other way around. Let's return to the opening number puzzle. Recall that no matter what two numbers that differed by 2 you chose, their product was 1 less than the square of the numbers between them. Suppose n represents the first number. The second number is 2 greater than the first, so it can be expressed as n plus 2. The number between the two is n plus 1. It's 1 more than n and 1 less than n plus 2. This middle number is then squared. Expanding each expression gives n squared plus 2n and n squared plus 2n plus 1, respectively. Notice that the expression on the right is 1 greater than the expression on the left. Or, in other words, the expression on the left is 1 less than the expression on the right. This proves what we noticed at the outset of this video. This can also be proved geometrically. The area of n plus 1 squared on the right is 1 greater than the area of n times n plus 2 on the left. Finally, we'll discuss how this video connects to your child's math curriculum. This video addresses several learning standards in the Foundations of Math and Pre-Calculus 10 curriculum. In content, we learned about multiplication of polynomial expressions. Your child will continue to work with polynomials in their study of functions and relations in later grades. Several curricular competencies, the doing of mathematics, could be experienced by your child in their classroom. Let's highlight a couple that were elicited in this video. We invited you to think with curiosity and wonder when we presented the opening number puzzle. Throughout, we visualized multiplication as the area of a rectangle, making connections between two-digit and binomial multiplication. These experiences are designed to deepen your child's understanding of the following big idea. The meanings of multiplication extend from numbers to polynomials. We hope that you enjoyed this video and found it helpful when supporting your child in their mathematics learning. Please check out the related video in this series, Factoring Polynomials. Thanks for watching.